In this video, we're going to go over moment of inertia and the angular momentum principle again, and we'll talk about this as it relates to an inclined plane with this problem here where we have a cylinder and we are applying an upward force on that cylinder on this inclined plane. Remember that all sorts of rotation happens in real life as well, and so we have propellers, doors opening, bending over and picking something up, an excavator, gear ratios, wrenches, we got the belts and pulleys in the engine, we have wheels on a car, yo-yo, and so on. So what we want to do here is apply some of these principles that we're learning in these problems to everyday life problems. And so the moment of inertia, we've talked about, we said, okay, we have this idea of the center of mass, which is like this weighted average of different masses, and so we add them up, multiply by the position, divide by the total, and we can get an expression for the center of mass. And when we have this idea of rotational resistance to motion, we have a way of calculating that as well for different objects with different axis of rotation. And we have a point mass just being mr squared, and you add them up, and the distances are measured from the axis of rotation. We have the parallel axis theorem and the perpendicular axis theorem, which help us when we're rotating about an axis which is a certain distance away from a parallel axis, or here with a perpendicular axis. And we have this angular momentum principle, which is really just kind of taking our translational or linear stuff and converting it over to angular or rotational stuff. And so we have motion as it relates to a circle with a certain radius. We have an initial position, an initial velocity, final position, final velocity. We have counterclockwise motion as being positive, clockwise as being negative. We have arc length that corresponds to that motion, which can be looked at. We have this idea of a right-hand rule, which is the cross product between two vectors producing a third vector perpendicular to the other two. And we have our 5 kinematic linear formulas, which we can convert over to angular formulas. It's basically just the difference of the radius. And we have the idea of centripetal force as well coming in here with uniform circular motion and non-uniform circular motion, and the force that you need in order to keep something in circular motion. And when we look at our units, they change over nicely as well. And when we look at our different formulas here, we can basically just plug in the angular form of those variables to get from the linear to the angular. And we have the momentum principle to the angular momentum principle, same idea here, and now we have this nice new angular momentum principle that we can use as a tool to deal with a lot of angular problems. And so remember that an inclined plane, since we have an inclined plane in this problem today, we have a situation where we have an angle to the horizontal. We have an object usually on that ramp here, and we have two main forces acting on this usually, where we have the normal force, which is perpendicular to the surface, and we have gravity pulling it both down into the ramp, but also down the ramp as well. And so we have an XY coordinate system that a lot of times we tilt, and we define this angle to be the same as the angle of the ramp, and then we can break it up into mg sine theta down the ramp and mg cosine theta into the ramp. And we can cross out the Fn a lot of times with the mg cosine theta. Those will be equal and opposite. And then the net force in this simple situation would just be negative mg sine theta. And so we'll see that here pretty soon with our problem. So for our problem today, it's a big problem with 3 parts, and basically we have a cylinder with mass m and radius r on a rough inclined plane here. And it's got a thin belt wrapped around it, and we're exerting a force F on the belt by pulling it up the plane. And we have 1/2 mr squared for the cylinder moment of inertia for that rotation. And for part 1, we're going to determine the magnitude of the force you must exert on this belt to hold the cylinder at rest, because clearly the cylinder would like to roll down the ramp, but we want to hold it at rest. And we're going to, for part 2, the cylinder is at rest on the incline, and we're going to begin to pull the end of the belt up the plane with a constant force, which is 2 times F, which we found in part 1 pretty much. And then for part 3, we're going to pull on the belt so that the cylinder remains at rest on the incline until this time Ti, when you abruptly cut the magnitude of the F that you exert in half. And so we'll take a look at that with part 3. So let's focus on part 1 first. And so for part 1, we're going to use the momentum principle and the angular momentum principle. And so hopefully you can start to see how these principles can be intermingled together. We're going to make the assumption that the belt is thin, and we can assume that the mass is negligible. And we're going to assume this coordinate system shown here, and like I showed you with the inclined plane, we get that mg sine theta down the ramp, mg cosine theta into the ramp. Just mg is acting straight down here, but we can see how when we start to put a force here of friction, and then the force applied here, which is at a certain distance from the axis of rotation, we're going to start to get some torque stuff happening, and we got that normal force as well. And so you can kind of see how, because it's a cylinder that's able to rotate, we have to use that angular momentum principle as well. It's not just a block that's sliding. So for this part 1, we need to determine the force, the magnitude of the force that we have to exert just to hold it at rest. And so we're going to use that momentum principle in equilibrium. So there's no net force here. And so in the x and the y direction, we can set them up separately. And so in the x direction, we have the force acting pretty much in the positive x, and friction acting in the positive x, and then mg sine theta is acting in the negative x. And that's got to be equal to 0. We can call that equation number 1. In the y direction, up we have Fn, and down we have mg cosine theta. We have to have that equal to 0 as well. We can call that equation 2. And then we're going to use the angular momentum principle, and so we know that the net torque has got to be equal to 0 as well. And now, depending on where we pick our pivot point is going to kind of determine this, but let's start by picking the pivot point in the center here. So there's only 2 forces that are providing torque. We have the force here that is applied that we have to consider, and also the torque from the force of friction. And so keep in mind, though, that this applied force is going to cause clockwise rotation, which is negative, and then the force of friction counterclockwise, which is positive. And so that's where you get that negative sign there. That's got to be equal to 0 as well, which basically means that the force of friction has got to be equal to the applied force here. So that's equation 3. Now, substituting equation 3 here into equation 1, we can arrive at this equation right here. And it's also worth noting that if we moved that pivot point, for example, down to here, then we can, in that situation, the friction would not be causing any torque there, and we would still get to the same result, though. So as long as you stay consistent with where you pick your point of rotation or pivot point or whatever you want to call that. So for part 2 now, we have the cylinders at rest, and we're going to begin to pull up here with twice the force that we exerted to hold it in place. So with a magnitude of F prime, which is equal to 2F. And so we got 2 different parts to this. One is what is the cylinder's speed when it is moved a distance d up the incline. We can use the idea of an extended system there. And then we can use the idea of a point particle system. For part B, we're going to figure out what is the magnitude of the force of friction here that the inclined plane exerts on the cylinder in this situation. So we're going to use the energy principle here, and we're going to assume that the belt is thin and the mass is negligible compared to the mass of the cylinder. We can say, okay, the system is the cylinder and the belt, and the surroundings is the ramp, the earth, and the hand or you. And for part A, we can use the energy principle on this extended system. And so on the left-hand side of the equation, we have the change in kinetic energy, which includes the translational and the rotational. And on the right-hand side is the work done. So we're basically using the work kinetic energy theorem. And so that's for part A, and then for part B, we can look at it as a point particle system. And so the left-hand side will just be the change in translational kinetic energy, and the right-hand side will be the work done by the net force. So let's get into how this kind of plays out here for part 2. Remember that the total kinetic energy is the translational K-trans plus K-rel, and K-rel is just the vibrational and the rotational kinetic energy, so you're basically adding translational plus vibrational plus rotational to get the total. So for part A, we have we're looking at the change in kinetic energy from translational and rotational is going to be equal to the work done by our force here plus the work done by mg sine theta plus the work done by friction. And so when we plug in here, remember we're starting at rest, so our initial kinetic energies, both rotational and translational, are going to be 0. And so we got 1/2 mv squared plus 1/2 I omega squared on the left-hand side of the equation, dealing with the energy. And on the right here, we have our F prime force times 2d. And so it says here F prime moves a distance 2d. And cosine theta, so the angle between that displacement and the force, is 0 degrees. The angle between mg sine theta and the displacement is 180. Cosine of 180 is just going to give you that negative sign. So it's doing negative work. It's resisting the motion. And we have friction, which is actually cosine of 0 as well, so that's up. That'll be positive. Cosine of 0 is 1. And we're good to go there. So when we do our substitutions, we end up with just basically plugging in, instead of writing F prime, we'll write 2F, instead of writing, which we can actually simplify further into mg sine theta. And then instead of writing omega, we can write V over R. Instead of writing I, we can write 1/2 mr squared. And so when we rewrite that, we get this here. We do some algebra, and we can solve for the velocity VCM. And that's basically what they're asking for part A. And we get an equation that represents that. And so for part B, we're going to use a point particle system. We'll just look at the translational kinetic energy equal to the net work. And so we'll basically just plug in similar to before, but we're not really looking at the rotation this time. We're just looking at F net times D. And so we got 1/2 mv squared equal to, we got F prime up the ramp. We got F of friction up the ramp. We got mg sine theta down the ramp in terms of our net force. And so we can solve for the force of friction there. And we can also substitute in the VCM from what we got in part A. And we can arrive at a nice expression here for the force of friction for part B here on this part 2. So on to part 3. Now we are going to basically cut the magnitude of the force in half. And so we're going to use the momentum principle and the angular momentum principle. And so and we're also going to assume again that belt is thin and we don't have to worry about the mass. The system is the cylinder and the belt. The surroundings is the ramp, the earth, and you. And what we want to do now is basically saying, hey, if we know the net force acting on the cylinder belt system, we can use the momentum principle to determine the change in its velocity, right? And what we want to do is figure out what the cylinder's speed is, right, at some later time tf. And so we'll kind of see how that plays out here for part 3. And so we're using that momentum principle, which is basically saying that the net force is change in momentum over change in time. And we're going to look in the x direction here, and our mass times our change in velocity here is going to be equal to F over 2 minus mg sine theta. So remember, we cut our force in half, so F over 2 is acting up here. And then we got mg sine theta, which is acting down, and our friction changed direction because we're beginning to roll down instead of up. And so our friction is going to be minus force of friction times our delta t. So basically we have our change in momentum there is equal to our F net times delta t. So we're just plugging in there, and we can kind of simplify that a little bit. And notice how instead of like in part 1 and part 2, we have force of friction acting down the plane because the cylinder is rotating counterclockwise now. So we basically have this equation number 4 where we just basically simplified it from there. And the angular momentum principle we can apply now. And we are looking at the torque now. And the net torque is equal to I alpha, and which is basically change in angular velocity over change in time. And so we can plug in also, if we wanted to, instead of angular acceleration, we could look at regular acceleration over the radius. And instead of looking at regular acceleration, well, we could just plug in change in velocity over change in time. And so this is basically a nice equation that we can consider for the net torque. And remember, we're interested in the cylinder speed, so we would love equations that have to do with V, right? And so we're trying to break everything down to V equations. And up here, remember, we had a delta V as well. And so we'll take a look at what's going on with the torque about the center of mass. Well, we have the torque coming from the force over 2. We have that is going to be clockwise, which is negative, and so that's a distance r away. We also have the torque coming from that friction, which is kind of reverse directions now, and so that is also going to be negative. And that's going to be equal to that net torque right here. So there's really only those two forces that are supplying torque, because the mg sine theta is acting right in the middle. And then we get a nice expression for the force of friction here when we solve for that. And we can call that equation 5 if we want, once we pretty that up. And what we want to do now is plug in, substitute equation 5 into equation 4. And so we have this expression for the force of friction. We'll plug that in up here, and we can simplify that down. And our goal is to try to solve for the speed, the cylinder speed at some later time TF. And so we basically are breaking this down, but we do know that the initial velocity is 0. So we can get rid of that, and we can solve for the final velocity is just going to be this expression right here. And so that problem illustrates how we can use the momentum principle and the angular momentum principle, and we can generate some equations, plug one into the other. Definitely a lot of algebra going on, but we can consider the translational and rotational motion of these problems, and also remember that this problem had multiple parts. So we had part 1, which we were just looking at what it took to keep it at rest, and then part 2 we were kind of pulling it up, and then part 3 here the friction actually switches direction because we're going to cut our force in half instead of doubling it, and so it really focuses in on how the torques and forces play into different aspects of these problems. So hopefully the angular momentum principle is making a little bit more sense now, and we will see you in the next one.